Hey, I wanted to share something with you, and I thought I'd put it into a little video because it really needs to be seen, to be appreciated. And here it is. This is what I want to show you. You can see by looking at it, I hope, that it's actually a spiral shape. See, as I follow up, this goes around, goes behind it. It's a spiral. And you may think, well, this guy took spheres and some glue and used his artistic ability, whatever he had, to make this by putting these spheres together, and so that it looked like a spiral. In other words, I tried to use my artistic eye to pull this off. But you would be wrong because the way that this was put together was following some simple rules of geometry and mechanics, which automatically turned this into this spiral as I glued it together. And the great thing is I didn't expect it. I didn't see this coming, but I think there's possibly some wonderful significance to it. So here's how this happened. I had studied Nassim Harameyn's course on unified physics. Anybody can go through that course for free on his website. And during that course, he spends a good bit of time describing the structure of space, the geometry of space, and he had learned about this originally from Buckminster Fuller, who had worked on it before, and he himself had made models of this space and using spheres, like I did with this spiral here. But the actual structure of space is something that Fuller called the vector equilibrium, and it looks like this. Maybe a better way to visualize it first off is to see this picture. It's also called the cube octahedron, and each one of these little points right here represents the middle of one of these spheres, the center point. But it's actually built upon spheres, not a thing with sharp corners, object like I show you in that picture. That just shows you the configuration of it a little easier. So I've been playing with these. I got curious because if you look at this, the structure of it is a combination of fours together and threes. It's all it is. Now, most people understand that threes put together makes a very stable structure. However, four put together is not so stable. It's not locked in like the three is. And just to demonstrate that, if I take a rectangle or a square, you see how these are free to move. So the most stable formation is the triangle. It got me thinking, I wonder what would happen if I started playing around with these things and putting them together, but I wanted to see what would happen if I limited my gluing together to just the threes. So I'm only using the most stable structure, geometry. So here's what happened when I tried to do that. Sphere number one, let's bring another one in, and it turns out in the structure space, these spheres, they are attracted to each other. They want to, say, stick together, you could say. Pop. So I have one, bring in another one, we have this, and then if we bring in another one, we're going to get this. Is the only way it can look is like this. And then if we start bringing in more spheres to connect them, first of all, we get this, which is basically the tetrahedron, the most stable three-dimensional form. And then if we continue on, let's say I try to continue adding, and the way I do it is I try to add it just in one direction to make it go out, but limit it to these threes, no fours, okay? Well, when I did that, after a little while, it became clear that something was happening. And after I did quite a few, it was quite obvious that I was making a spiral. Spiral, does that remind you of something? How about a vortex? So to make it more interesting, in the class on unified physics with Nassim Haramein, he a couple times gives an analogy. It's a fun little analogy of, think of a bathtub, rubber ducky in the bathtub, and somebody pulls the drain in the bathtub and the water begins to drain. And then what do you get? You get a whirlpool, right? Everybody knows the whirlpool in the bathtub. His point in this analogy was that what's happening is you're having a density differential. So there's one density in the bathtub water, and then in the drain, the density is much less, thus the water is draining out. It's a density differential. And in this density differential is what causes the vortex, the whirlpool. Now, the thing about a density differential that everybody sort of understands, I think, naturally, is that it always wants to even out. The higher density wants to even out with the lower density so that it's no longer a difference in density. And this is how you can get a directional flow. Think of in weather, for instance, high pressure air and low pressure air. What do you get? Wind. And the wind goes in a certain direction, right? Or take an electrical circuit. If you've got high density of electrons on one end and low density on the other end, you have made a differential, and you have what they call it potential. I guess you'd be voltage. So there can be a flow in a direction from the high density to the low density. So I can apply that same density differential idea to my little experiment with my spheres here. Okay, so here's my baseline of spheres, let's say, and it's all surrounded by other spheres somewhere. And let's say there's a density differential. Let's say higher density is up here above. Let's say lower density is down here. So that being the case, from what I said previously, we understand that it's going to tend to set up a flow, a direction of movement from the higher density to the lower density. So we have a direction. And now picture these spheres coming to this baseline here, and it's coming from a certain direction. It's going to link up on here, starting with that. And then the next one's going to come, and it's going to want to link up to the easiest place for it to connect based on the direction of its approach. And this is what I ended up with. This is my whirlpool in the bathtub, you might say, and it might have other significance too. Okay, so I wrote this down based on everything I learned from Nassim Haramein's unified physics, and also from Marshall Lefferts' book Cosmometry. Those two guys work together a lot. And what I wrote was that every realization of matter or energy from the vacuum space into the physical realm comes through a vortex of yes. In conclusion, I just wanted to say I don't really have the background to try to work putting together an actual 0 point energy device. So I've just been studying in this theoretical realm of what can be involved in making this happen, and just hoping that something will make a connection between the theoretical and the practical at some point. I have no idea if this would be helpful in any way, practically speaking. If nothing else, it's an interesting thing to look at, and at best, maybe it'll help put something together for somebody that's working on the nuts and bolts of putting together a 0 point energy device. It's been a week or two since I recorded the first part of this video, but there's something that has been bothering me a little bit in the back of my mind ever since then, and that is the fact that a spiral is not necessarily a vortex, right? A spiral is something that looks like a vortex, might be related to a vortex, and maybe a vortex is a spiral, but a spiral is not necessarily a vortex because a vortex is moving and spinning, and a spiral is just the model, right? But a little while ago, it just came to me that a spiral is indeed connected with the vortex. And I think the reason I didn't see it is because I was so pleased with what I had found already, I just kind of stopped there and rested instead of going forward. So you remember how I came up with the spiral before we had pressure, you could say, because of the density differential causing things to move in this direction from higher to lower. And we brought the sphere in right toward the center, and it would tend to land right in that spot where it's supposed to, where it can stick the easiest and be stuck there. And that's how we could just continue to build this thing up. But let's just leave it right there, and let's just say done with that for now. And let's say it's just a spiral, it's not a vortex. Okay? But here's the thing that I found quite exciting. We've got a spiral. We've still got the pressure coming down. There's not just one sphere here. It's all surrounded by spheres, and they're all tending to go this direction, and they all also have the tendency to be caught into these grooves where they'll stick. So forget about the one in the center. Let's go to the next of the onion, the next layer, let's say. There's those spheres that are right outside the center, and they want to come down too, and they also want to stick. So there's two forces. A force down, I'm saying down, not necessarily down this direction in this case. And then the tendency to stick in these places. Keep in mind when I say stick, I'm talking about the bringing in of another sphere, and it's going to connect into the center of three others. So right in the middle there, basically talking about the triangle, and then as a two-dimensional thing, and then bringing one more in, making it a tetrahedron. Very stable connection. So here we go. This is a sphere that's more off the edge, and it's going to go off the edge, and it's going to want to come down, and it's going to want to stick somehow on here. So here it comes. I want you to see what's going to happen. As it comes down, my hand is probably in the way. I don't know how to do this. It's going to come down the side. And then there's these little spots in here where it's going to want to stick. So it's going to tend to stick there, but it's also being pushed down at the same time. So it's going to go there, but then it's probably going to roll on down to the next spot. And if the balance of forces is proper, it's then going to roll down to the next spot like this, and now to the next. And can you see what it's doing? It's basically rolling down the side of this spiral. And as it's doing it, it has no choice if it's going to do that, except it's going to go follow the groove between these things, and it's going to move in a rotary fashion. So what I'm saying here is now we've actually got motion. We've got something moving in a direction and spinning at the same time. And I think what we've got here is a possible quantum mechanical explanation for how a vortex works. I got a couple other things here I thought were interesting you might enjoy. This is, I showed you earlier, called the vector equilibrium. It's the cube octahedron. And there's a whole thing about the fractal nature of all these things. And probably most everybody knows what a fractal means. Probably seen videos that demonstrate it. Anyway, this is fractal. In other words, there can be smaller versions of it that are the exact same thing, or it can become bigger and produce the same shape, basically. And that can go to infinity, basically, as bigger or smaller. So something interesting about this guy here is that there are 12 spheres in here. Actually, though, there's 13 because there's one in the very middle also. It's very interesting, the number 12, when you start to look at it, not just in geometric shapes, but in other things, music, and so forth. Music is one of the most in-your-face fractals that we are presented with on a daily basis, but it's so common that we just take it for granted. There's a note here. If you go up an octave, guess what? It's the same note, except it's in a higher level. Another octave, it's the same thing. Fractal. There's 12 here, and if you look at the spiral here, I wanted to see, because it spirals around rather slowly as you build this thing, I wanted to see how many spheres it took before the sphere went all the way around. Turns out it's exactly 12, which is quite significant. So this one is the first, say, if you follow it around, it ends up to this one right here. It's 12 exactly. Very cool. If you think about that in terms of music in a keyboard. And then there's 12 notes in every scale from one octave to the next. it's fractal. It's the same thing in music. So this is a very interesting correlation. We have 12 of these that go around. There's a lot of details we can go into, but it's too much for here. Get up to here, you could say that you've gone an octave, and that to continue on would be a next octave. Very interesting. This, you might say, well, that's 13, it's not 12. Interestingly, this could go bigger and go up an octave, you might say, and be a bigger version. You could also go down. Well, there's only these 12 balls, but that ball in the middle sphere somebody correct me if I'm wrong, but I think that actually represents a lower octave or a different octave in the opposite direction. Quite interesting.